is to formulate a script to implement this matrix, and this matrix solves this differential equation using the method of finite differences. We did this before, but with the boundary condition that t0 is 40. Now, instead of this boundary condition at t0 equals 40, we instead are going to say that dt dx at x equals 0 is some constant ta prime. I'm just going to choose 0 for this constant because, again, the no flux boundary condition is the most common one. I'm going to start with the script. What I did was I took the script to solve the previous problem, 27.3 from the textbook, and I just I did a save as, and I added the words no flux to the name. So at present, what you see on your screen is the solution to the problem that has the original boundary condition of t equals 40 at x equals 0. So what I want to do is modify this for the no flux, and I'm going to start by deleting the alternative formulation. So we're just going to work with the original formulation, which I think more closely resembles this one, because at the end of the domain at x equals L, we move the 200 to the other side of the equation. And so notice that almost every line of the equation here has -1, 2.04, and -1. 2.04 is C2. So we're going to stick with the original formulation and then modify it so that it handles a bigger number of unknowns. Originally, T1 through Tn minus 1 were our only unknowns. In the step size of 2, that's only 4 unknowns. So we're adding 2 unknowns to this problem. So instead of a 4 by 4, we have a 6 by 6. Or as a n minus 1 by n minus 1, we're going to have an n plus 1 by n plus 1 matrix. And also the pattern is really similar except for the first row. So let's modify this. Okay, so the matrix n is going to have m is going to have dimensions n plus 1 by n plus 1. The matrix B is going to be n plus 1 by 1. In most cases, it's going to be 0.8. That's what C1 is. Let me change the step size. So that corresponds to an n of 5. And I'm going to delete this. We're going to come back to that, the first row. Let me just okay, so I just made a little note to myself to come back. And what we need to do here is we're going to have I equals 0 starting at t0, and we're going to go to n minus 2, 0 to n minus 2, so 0 to t0 to t3 in this case. Okay, the diagonal is going to be C2, so the row is going to be I plus 2 in the beginning. The second row corresponds to I equals 0, and whoops, I changed the wrong. That's I plus 2, and we're going to go from I plus 1 to I plus 2, and then I plus 3. So columns, so when I is equal to 0, this is columns 1, 2, and 3. That looks correct. So this should populate the matrix from this row to the second to last row. So now we have to consider the last row. That corresponds to I equals n minus 1. And the diagonal is still going to be I plus 2. So we're going to start, and okay, so I plus 2 is going to be the same as n plus 1. Okay, that makes sense. So this is going to be I plus 1 by I plus 2. That's the diagonal. And this is going to be negative 1 C2, and then B of I plus 2 comma 1 is going to Tn plus C1. C1 is 0.8, Tn is 200. So that should work. And then when we solve, we're not so interested in t negative 1. That's a virtual point. So we'll start off by solving this, and so the solution is going to have t negative 1 to tn minus 1. So we'll just add tn to that. And then what I'll do is I'll say t series equals t series 2 colon end. So I'm just going to drop the first number so that t0 is where we start, and then x is going to be 0 through L like we had before. Okay, so our last step is to implement this boundary condition. And let me add ta prime as a constant equal to 0. So what we're going to have is an m row 1 and then columns 1, 2, 3 equals negative 1, 0, 1. And we're going to say b 1, 1 equals 4 times ta prime. Going to be 0 in this case. So let's run this. Let's run it and see. Okay, so we got something that looks promising. We have 200 degrees here, just like we expected, and we have something that's starting to level off here. So that does resemble a first derivative equal to 0. It's not perfect, but that may just be because our step size is too large. Let's actually compare the matrices. Hello. Okay, let's display M and B. This does look right to me. Let's undock it and compare it with our notes. How do you undock? Here. Okay, so M has a negative 1, 0, 1. It's a 6 by 6. That looks correct. This pattern is negative 1, 2.04, negative 1. That looks correct. At the end, you just have negative 1 and 2.04, and then you have, remember I set ta prime to 0, so 0 and then 0.8 all the way down, except for 200.8 at the end. So it does look like this worked. And so the last thing I want to do is reduce the step size. Let's make it 100 and see if we can more clearly see the temperature profile leveling off. That does not look like a step size of 100 to me. Did I just change it to 10 instead of 100? I hope I didn't. Hold on, I hope I didn't change the wrong number here. I think that's right. Probably not worth displaying M and B anymore. All right, that looks much more smooth. So you see how you flatten the temperature profile at x equals 0, which is consistent with the derivative being 0 at x equals 0. and then it still rises up to meet 200 at x equals 10. So I think we succeeded.